Dobrze. Three. What about words? Hello. Okay.
Didn't come for lab number 3. You have to do lab number 3. It's about finding the electric line. Just like the first one. Like the first one was a bit different. No, there's no problem. So for you, you thought it's finished. I'm sorry.
Me, I was reading late, so I just wanted to get it. I'm like, what?
Yeah, I really don't need pills. I told you people there's a lab work.
Yeah, cool.
Yeah, it's really there. But I know some of those people don't mostly mind. Oh my goodness. I know, I'm not sleeping. But what are you thinking about? Don't worry. It's easy. You don't have to do any calculation. You just have to do it.
That's one high. You don't have plastic again. But that go.
But that was not. It was not staged.
Yeah.
That was so cool. It has fast.
What's the line? Now, why did they draw the line? So
They don't want to do that. This is
my excuses. They cheated. Just like us winning that game against the Coventry City.
Yeah, I think that was also.
We didn't deserve that win.
That was so
I was even proud of myself. Didn't thought we had lost because when they equalized the fourth goal, the one that was rolled out. I mean, locked out, and then I went, I really need to do something else. And I came back, I just saw the post, my face was all over. Sign was, huh? No, that goal was ruled out. Okay. We don't deserve that win. No, I'm going to beat Man City. I want to
whoop you.
They're going to beat Blue Black.
They're going to beat you with blue black. No, blue red. That guy, what's the problem?
We're waiting someone.
Yes. What?
And silence.
No, next week is online.
Okay, I will start.
I don't know.
I don't know. You can see the professor.
You can see the professor.
Well, there's this guy who just came today. Obviously, because he was told not to do the lab, so
Yeah.
and there are other people.
But he wrote his name on the protocol, on the stuff.
You know his name, huh?
Yeah, and the professor signed. So that means there is no protocol. This lab is called COM, but there's no protocol. Come and do us.
Oh, I can write something.
Why did you do
So, what I got for today? Something nice and fine, called pulse modulations. The general idea, you may have a sequence of pulses. With tau length of the pulse and let's say 0 period time. How can we use it for information transfer? What can we do? We can use pulse amplitude. It will be PAM, pulse amplitude modulation. We can use pulse shift. For example, this can be phase shift modulation, or we can use frequency to put the information in. We can use PFM, pulse frequency modulation, or angular modulations. They are very similar. When the pulse frequency is your information, or you can use this tau to encode information, and it will be PWM, pulse width modulation. We need to understand, become acquainted with spectral characteristics of all these techniques. But for beginning, we may need spectral characteristic of pulse sequence itself. So let's assume something like this. I have a pulse sequence, tau 1, tau 2, amplitude, let's say E, and, it repeats with period T0. This point will be tau 1 plus T0, and this point tau plus T0. Yeah, here is my sequence. Nice sequence. What will be mass description for this sequence? Such sequence can be written as. Can I erase it? No one wishes to draw the sequence. This can be written as equals to E when tau 1 plus M0 time tau plus MP0. Here I should write 0, tau 2 plus MT0 time, and here I will have tau 1 plus M plus 1 T0. Here M is an integer from minus infinity, 0, 1, infinity. M is integer. Here is my description for my sequence. So I would like to obtain a spectral characteristic for this. Any periodic function can be substituted with a Fourier role. Minus infinity to infinity, a power J E double P time. Yeah. When AK is a complex amplitude of K, harmonic being E double P divided by repetition period. In general, I'm repeating, each complex amplitude can be found as 1 divided by minus by half my function a power your double p divided by period time, and I should integrate in time. For the sequence of pulse, best way to obtain this rule is to use a technique developed by Whittaker. Is to not use sine or cosine, but use a special set of orthogonal function sine kx divided by kx. For the sequence of pulse, compass amplitude of harmonic will be E tau divided by T0 sine of K double P divided by T0 tau divided by K double P by half, and here also should be by half. Look closer at this formula. What kind of spectrum will we see? What your Facebook tells? What kind of function is it? Any idea? Since? Am I correct?
Sync function.
Sin or sin and C.
S-I-N-C.
Sin, integral sign. Since it looks like. Yeah. Actual. This signal spectrum, I can. Okay. Signal spectrum in frequent space, or double P divided by T0 multiplied by this signal spectral function, or double P sum from minus infinity to infinity, a delta. Sorry, here should be also a 0. Delta functions omega minus double P T0 R. Funny thing, isn't it? What it will be? When you divide sine x by x, at some moment, what you will get? Like a needle going up, yeah? Since function. This one, yeah? What you get from since function? Periodically. Here, look here. It's like a set of needle on a particular frequency And these frequencies are function of a repetition period. Actually, it's like infinite set of very thin needle. Very specific kind of spectrum. Yeah. We can try to play assuming signal like some m started from minus infinity to infinity, delta function m d. What's this? Ultima of all pulse sequence. Why ultima? It's infinitely thin. It's a sequence of needles in time. Infinity thin needles with the period of t. It's, let's say, ultima short path of all pulse in this world. Why you may be interested in such sequence? Analog to digital conversion. Absolute sampling will be such sequence. If you multiply such sequence with your signal, it's an absolutely fast sampling. Ideal sampling. For such sequence, I can write a Fourier rule. It will be 1 against period equals minus t by half. T by half. Delta function a minus dot k double p time d time. It's very easy. It will yield 1 against period. Delta function takes all frequencies. What will be spectrum? The whole spectrum equals double p period spectral function of my signal, or double p divided by period sum minus infinity to infinity of omega k double p we will see infinite sequence of equal infinitely thin spectral lines. Sequence of infinite thin pulse in time in frequency space also represents like a comb, infinite comb of infinitely thin spectral line. Returning to my pulse sequence, if I have sequence of pulse, not infinitely thin, but with something realistic. If I have something like this, and they have amplitude E. What will I get? Again, your favorite sinc function and kind of comb of delta functions. Look. I will get. So, spectrum of the signal will be double E P divided by T0 sum from minus infinity to infinity sine of K double P T0 tau half and divided by K double P T0 tau. And this should be multiplied by delta function of omega minus K double P divided by T0. One second. This also should be by half. Yeah, now it's correct. Trust no one. Nice formula, isn't it? I can approximately draw it. How it should look. Very approximately. Frequency. This guy is border line. This 0 point is double P divided by tau. This is 4P divided by tau, 6P divided by pulsar ends. Okay, minus double P divided by tau. It's a borderline. Inside fits the step of this step is double P divided by repetition period. Zeros is one trick. One interesting moment. Distance between spectral line is determined by pulse repetition period. But zeros are determined by pulse length. And this point, double P A0, this point is double P A1, this point, double P A1 conjugated, double P A2 should be somewhere here. This one, double P A2 conjugated absolute value. Something like this. Nice chart, isn't it? I knew people who are ready to hang because of this chart, and you will understand why. What's the meaning of this chart? Now see. I would like to do one thing. This thing has, it's in general, it has a zero or DC regime at a center. Because for people it's easier to operate with positive frequency. I can take a real part of it to work only with real frequencies. To take a real part with correct account for zero offset. For correct account of zero offset, I will write like this. Tau 1 divided by T0 multiplied 1 plus 2 multiplied by sum of starting from minus infinity to infinity sine of P double P divided by T0 tau 2 minus tau 1 divided by half, or divided by K double P T0 tau 2 minus tau 1 again divided by half. If you think this is all, no, this is not all. Who writes something like this? We'll continue. This is your since sine of kx divided by x. Can I erase? There is more. I need also write cosine of P double P divided by T0 minus plus tau 1 divided by half. 1, 2, 3. Nice formula. Nice. I like things like this. Actually, this form, with correct accounting for tau offset, isn't very popular. Also exists version of two signs. Signal can be represented as what I'm doing, tau 2 minus tau 1 divided by repetition period plus 1 divided by kp sum 1 to infinity. Here should be sine of k omega 0 multiplied by minus t1 minus sine of k omega 0 t minus tau 2. Second, here omega 0 double p divided by t0. It's an angular frequency of our pulse sequence. So, spectrum of my sequence. Again, E tau 2 plus tau 1 divided by T0. 1 plus double sum, like from 1 to infinity. I'll use positive frequencies. Sine of k omega 0 tau 2 minus tau 1 divided by half. Whoops. Divided by k omega 0 tau 2 minus tau 1 divided by half, and multiplied by cosine of omega 0 t minus tau 2 plus tau 1 divided by half. Whoa. Nice formula. What we will see yellow sequence, red sequence, red spectrum. This nice formula I can try to draw it. Frequency it's a borderline. This point is m double p divided by tau. Okay, this one is double p divided by tau. 2 double p divided by tau. 3 double p divided by tau, and so on. These are 0 points. 0 points are at the double p divided by tau. Inside, you will see a spectral lines. This thing will have spectrum of thin lines. At omega 0, double omega 0, triple omega 0, where omega 0 is double p divided by t0. 4 omega 0, and so on. See that the moment, this borderline is defined by pulse length, while spectral lines are set by repetition period. Look here, I have an example. Yeah, I have a pulse sequence. Now its field, it has a 50% field. So tau 1. Look what will happen when I change the symmetry. At this moment I have 20%. Tau is 20%. Look what happened with the spectrum. Red line is a spectrum. You see what's going on? Whoop, 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 whoop. Look, I'm changing the field. 20, 40, 47, 50%. You see these waves? No, they no longer appear. In opposite direction. 80. Whoop, whoop, whoop. And do you see how long this tail in frequent space? Where are my cursors? My signal is 100, repetition rate is 100 kilohertz. 100, 1 megahertz, 4 megahertz, 5 megahertz, and still trailing. From the pulse sequence of 100 kilohertz, you see trailing 9 megahertz and still present. You see how wide is spectrum of the signal. The screen spans up to 12 megahertz. You can still see trailing of the sine x divided by x. Okay. And clearly, you see, these zeros are defined by pulse length. Okay, let's go forward. Now let's try to see what will happen if we use this sequence for transfer of something. Let's say come on. For simplicity, this is my signal. Simply sine of omega s Very simple signal. I will try to use PAM, pulse amplitude modulation. This is my signal. 1 plus Vm. Wait 1 second. This is not correct. 1 second. Here are my pulse with the repetition T0. I will draw in orange. Okay, this one is a repetition period and tau 1, tau 2. This one is T0 plus tau 1. This point T0 plus tau 2. See, pulse sequence. When inside the pulse, its amplitude follows my signal. Can I push a button? Hey, sorry. Look at this button. Oh. Well, something like this. Nice cup. What frequency do I have here? Maybe 5 kilohertz will be better. My signal, modulating signal is 5 kilohertz and signal don't like me. Where is 1 second, I will prepare my tools. And you can try to think where such signals. What is it? Where you can see such signal? What can it be? 1 second, I'll be back.
Makes me see like that.
need a freezer. The signal is refused to freeze. Still not good as I would like it to be. Signal file shape. Can you please stand still? Yeah. Frozen signal. What can it be? Where such signal can be expected? Point number 1, image sensor. Image sensors produce amplitude modulated signal. Pulse for each pixel and its amplitude, the pixel brightness. But that's not all. When you have some physical values, I don't know, S1, S2, I don't know, multiple sources, and you need to process them with your microprocessor system. What you need to do? You need to digitalize them, yeah? You need ADC. You can put ADC for each channel, analog to digital converters. But high precision converters were a high price tag. So it's nothing unusual to use multiplexing. Multiplexers, ADC, processing. here is the point when you will see pulse amplitude modulated signal. In some old time existed system. Now this path of signal is very short nowadays. But in older days there was no digitalization at all. Signal was sent to control panels via single channel. See, if you have a transfer medium, you want to use it for multiple signal, multiple information source, you can divide it or by frequency or by time. Yeah? Yeah. If you use time spacing, you will see multiplex signal. For example, network. Should be network. What's the name? Ethernet cable, and the network should be, appears to be an Ethernet, yeah? How Ethernet, PC, how they are spaced in this media? How many cables I have? One. How many computers I can attach? Many. How they share this cable? In time. CCMA, CD. Yeah. Access, separation time. At a lower level of Ethernet, you'll see time sharing, not a frequency. TV channel broadcasted by coaxial are divided by frequency. Time multiplexer. Here, the first simple idea of time multiplexing. You see this nice sequence? Frozen. I use a very simple signal. S maximum sine omega s containing only one frequency. Tau 1, tau 2, tau 1 plus T0, tau 2 plus T0, and so on. Here I have a simple model where inside pulse, inside one switch of multiplexer, signal follows the original. It's not must. Another model is with sample and hold. For this line, I can write what? E 1 plus M capital, which is depth of modulation. I'm changing the M parameter. depth of modulation. Okay, come on. Stand still. Sine omega s. In case of symmetry, in case this equals to this, I will get something like this. I'll need to obtain a spectrum for being E1 plus modulation sine of omega s time minus tau by half plus m t0 time tau by half plus m t0. M will be integer. And 0 when time is tau by half plus m t0 time minus tau by half plus m plus 1 t0. Here is a very simple expression of the yellow line. I assume it as m1 relative. Can we now get expression for the red line? Wow, what a beauty. Can we get expression? We need it in form of Fourier role. So, if I wrote it correctly, it should be 1 plus m sine omega s time tau divided by t0 multiplied by 1 plus double sum, which starts from 1 and ends at infinity, sine of t double p t0 tau divided by half divided by k double p t0 tau divided by half. And that's not all. Cosine of k double p t0 time. One bracket ends, second bracket ends. Nice formula. Yeah? You like this formula? Appears to be something from a nightmare. No, it's a simple formula. What do we see here? This will get us kind of set of needles. 0 points for these needles will be where? In n double p divided by tau are 0 points for this needle. One moment, I will switch myself to. I'm changing tau. See what's going on with red line? 0 points are moving. Now it's 20%, 26, or 20%. 40, 50. Here is tau is 1/2 of the t. See what happens with 0 points. Again. %. Tau is 20% of T capital. See therefore where the 0 points are. Tau is 57% of T capital. And what about this one? The second term, we saw this when we speak about unmodulated sequence. But what about first term? Do you see something familiar in it? No? Okay. 1 second. I will rewrite it. I can rewrite this. I will make it clear. E tau divided by T0 1 plus modulation depth sine omega s plus double sum. It starts from 1 to infinity. Sine omega 0 tau divided by half divided by omega 0 tau by half multiplied by cosine k omega 0 time plus m by half multiplied by sine of k omega 0 plus omega s time minus sine of k omega 0 plus omega s time one more, and one more. And what about now? Switch to show it. Huh? Something familiar? Omega plus or minus. I found an error. Minus. Omega plus omega signal, omega minus omega signal. AM signal. Amplitude modulated signal. One moment, I'll draw. It's theoretical. Where's my big thing? Oh! Board from protective relay. That's a memory program input, analog channel MUX and ADC. These two, it's a ranging amplifier and this analog to digital converter. From this point to this point, something like this can be observed. Frequency. Now, it's emerging line. This point is double P divided by tau, and 2 double P divided by tau, 3 double P divided by tau, and so on. This is borderline. Inside, I need to draw, these are spectral lines of my pulse sequence. Omega 0, double omega 0, triple omega 0, 4 omega 0. Yeah. Nice. And around them omega 0 plus omega s, omega 0 minus omega s, double omega 0 plus omega s. This one will be double omega 0 minus omega s. And so on. The ratio is modulation depth between them. Four omega 0 minus omega s. This one will be 4 omega 0. This is plus, this is minus omega s. That's what you will see in theory. You see spectral line of modulating signal around each needle. I'm not sure, but let's try. Let's try to enlarge one of these peaks.
One.
For example, U. Ho. Do you see what I see? Spectrum of this signal, now it's one spectral line, around each of the spectral lines of sequence. Do you understand how ineffective is this way? When we speak about channel usage. At each frequency, you saw this tail up to 5 megahertz, even far. I saw it even at 7. At each line of the tail, see I enlarged. I have spectrum of my signal. Possible. Maybe this is not spectral. What's the spectrum of this signal? What's the spectrum of such signal? Yeah. Maybe your phone can answer. What's the spectrum of the signal?
He's on that side, hasn't he?
Huh? If this amplitude is E, it will be 4E divided by P multiplied by sine double P plus 1/3 sine 3 plus 1/5 sine 5 double P and so on. Omega plus 1/3 of triple omega plus 1/5 of 5 omega plus 1/7 of 7 and so on.
Is that the Fourier transform?
Yeah, it's Fourier. I started the idea of Fourier transform from this. Where is my magic?
We're going to talk about Fourier too.
Oops. 0, 3.
Fourier.
And here it is. Can you see it? Okay, blue line, modulating signal. Yellow line, modulated pulse sequence. Red line. One second, I will show it in detail. You see? These nice peaks. But around them, enlarged remember amplitude modulated signal.
Goodness.
Original signal 1 omega s, 1/3 triple omega s, 1/5 5 omega s. Amplitude modulated signal would be omega 0 carrier, modulation depth by half, omega 0 plus omega s, omega 0 plus triple omega s. This one will be omega 0 plus 5 omega s. On the opposite side, again, m by half. This will be omega 0 minus omega s, 1/3 omega 0 minus triple omega s, and here small, 1/5, 20%, omega 0 minus 5 omega s. That would be amplitude modulated signal in frequency. Yeah? If you switch to palm, you get the picture of amplitude modulated signal at each line of pulse sequence. And around, I will draw them in yellow. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. What can you tell from this picture? From this point? But it's yellow. If you try to use multiplex channel, sampling rate should be at least twice higher than the high frequency of your signal. Or at this point they will overlap. If you would like to transfer 10 kilohertz signal, you need at least 20 kilohertz rate of your sequence, or they will overlap. See, nice? AM signal around each of the line.
So what does this do?
Huh? A model. Nice spectrum of the sequence, pulse sequence. And inside at each line, come on. Inside at each line, oops, here it is spectrum of modulating signal. Oops. Okay. I continue with amplitude modulate signal, this version is simple when you see each pulse follows the signal. There is another version with sampling, sample and hold. Version of sample and hold, for example, this is signal and pulses go like this. One more. Oh, something like this. Idea what there is a hold and pulse remain like analog to digital converters with sample and hold. Version of pulse amplitude modulation with sample and hold device. Okay, this is fat pulse. Time. So for such, I'm not sure you ever will need it. This will play if you analyze electromagnetic compatibility of your analog to digital ADC converter. In old time, I remember when ADC was like this modules, and there was a cable from sampling unit to ADC itself. Okay. This can be written as with sample it will be E tau divided by T0 1 plus modulation depth sine omega S tau by half divided by omega S tau by half sine of cosine time plus double sum from 1 to infinity of sine omega nu 0 tau divided by half divided by omega 0 tau by half cosine n omega. Wait 1 second. K omega 0 time plus. I will continue on next board. Will continue. Can I go forward? Nice little formula. Plus half of modulation depth sine of k omega 0 plus omega s Yeah. Divided by half, divided by k omega 0 plus omega s tau by half. This should be multiplied by sine of k omega 0 plus omega s time minds will continue. Yeah, it's a free table formula. That's what happens when you put sample and hold. Minus sine of k omega 0 plus omega s time divided by 2 stop can be, should be tau k omega 0 plus omega s tau should be divided by half and multiplied by sine of k omega 0 minus omega s time. Up. Tiny formula. I have a chart. Oops. Can I draw it? Well, I can try. This will be frequency. Whoop, whoop, whoop. Borderlines. 1. Okay. 2. Between this line are half of modulation. Okay, next, thin spectral line at omega s. Next, line at omega 0. Do I have more colors? This is omega 0 plus omega s. And this one, omega 0 minus omega s. Right here. Again. Whoop. 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 Double omega 0 plus omega s. Double omega 0 minus omega s. And this one is omega 0. Yeah. One more. Triple omega 0. Triple omega 0 plus omega s. Triple omega 0 minus omega s. And so on, so on. So on. here how it looks to borderlines. What's interesting in such case, you will get asymmetric side bands. Sample and hold produce asymmetric side bands. If you will work in communication industry, maybe you will see some elements of all discussion. What is the profitable way to transfer data or voice uninterrupted or in bursts, in pulse? See, here is one important moment. At the first look, pulse are more profitable because you have concentrated energy. And you can work in bursts. But if you use pulse sequence, spectrum repeats on each spectral line. You will have much wider spectrum. And this means what signal to noise ratio remains the same, uninterrupted or in pulse. But for microwave, for high frequencies, starts playing the bandwidth of your receiver. And appears what if your receiver is very precise, they are equal. But if you have an imprecision, imperfection in your receiver, and it cannot hold a narrow frequency band, this method is more preferable. Okay, do we need to take a break?
Yes.
Yeah, because I would like to speak on frequency and pulse width modulation. More modulation for God of modulation. Okay, let's take a break, yeah? More modulation for God of modulations. Small, nice formula.
kopsavilkumus droši vien jāpārskata, ka tie iet pa lielam iekšā sistēmā, nu viņus laikam var mainīt,
Laikam to pēc tam nevar mainīt.
Bet A daļā teorētiski vismaz seminārā minēja, ka viss, kas ir tā daļā, to pēc tam īstenībā nevar. Nezinu. Un pēc keyboardiem un kopsavilkumu viņi it kā meklēs ekspertus pēc tam. Nu, it kā tad to B daļu, it kā pirms fināla apstiprināšanas, ka vēl var tur mainīt un tā tālāk. Bet es domāju, varbūt tos kopsavilkumus var ātrāk skatīt. Nu, katram gadījumam es viņus aizsūtīšu, kaut ko es atcerēju tur noteiktajā apjomā.
Būs. Jā, vajadzēs parakstīt. Es paņemu šī te kārtu un viss padomus jaunai valdībai jāparakstās. Jāzvēr. Un es jāzvēr uzticībā pārreģistrē. Tad būs jauna vadība. Kaut kas būs. Nu, ikibāna. Ikibāna. Un šī te, tu te izdomās. Ko 220? Blok kontakti, ko saistīt. Un tev ir modulated. Jā.
Let's go forward. More foremost forgot of foremost. What can be done with the pulse? Let's see. 2, 1, 2 is original sequence. That's the next one, for example. Yeah. Next pulse will go. Next pulse will be here. Pulse is shifted by M, S. Idea, what you can encode your information as a shift of the pulse. For negative, it will be like this. So if this one was 0 for the orange one, I need to write T 0 plus M S, let's say this is 1. Encoding with the shift of pulse. The same, actually the same spectrum, you can use small difference. This will change only pulse position. Or you can use pulse frequency to transfer your signal. Where such signals are used? Or around automotive industry very likes this kind of things. Airflow. You know what? Each car needs an airflow sensor. Airflow sensors very often produce frequency as a function of airflow. Temperature, air temperature, oil temperature. Many cars even use throttle position. Throttle position, when you think on what you put your feet on, sends its signal as a frequency of pulse. Are resistive, but are sensors that send pulse frequency. Very popular thing for all kind of sensors, because it is quite noise resistant and very easy to get into a cell. You don't need an ADC for each channel. For air temperature, no ADC, you just need an optocouple at the AMC border of your ACU. So here will assume S max 1. So here tau 1 will be tau by half plus m sine omega s. I'm assuming signal as sine omega st. Tau 2 will be tau by half plus m sine of omega s t minus tau. Now I can write my pulse sequence. It's equals to E if time tau by half plus m sine omega s time plus m t0 time up continuous tau by half plus m sine of omega s minus time plus m t0. Here m capital is an integer and equals to 0 when tau by half plus m sine omega x means time plus m t0 time minus tau by half plus m sine omega s time plus m plus 1 t0. Oh, very simple. Formula of my sequence. Next step, I need to decompose it into Fourier law again. Again, I need sine e. I will use sine kx divided by x. What will I get? My signal can be substituted by E multiplied by tau divided by 0 minus double modulation depth divided by period sine of omega by half cosine of omega s multiplied by tau by half plus 1 divided by tp sum from 1 to infinity of k double p t0 time plus tau by half minus m sine of omega s minus, I will continue on the next plot. Small formula. And it's for simplest possible signal. One frequency. Can I erase? Minus sine of k double p P0 tau by half minus sine omega s. 1, 2, 3, 4. Yeah. Nice formula. Very nice formula. I like it. We need to do something with sine k double p time in t minus m sine omega st. Blah. We need to do something with it. There is idea, and you know what kind of idea? Idea apply technique of frequency modulated signal. So to open this sine of the sine, you can use a Bessel function. It will yield us E tau divided by T0 minus double modulation depth divided by T0 sine of omega s tau divided by 2 multiplied by cosine of double p divided by T0 time minus tau by half plus, may I left it to the second book. Plus will continue. Tiny little formula. Formula continues plus sum to infinity of the m should from minus infinity to infinity kp here is a Bessel function of K modulation depth double P divided by T0 multiplied by sine of K double P divided by T0 plus M omega S should be divided by half and multiplied by cosine of, this is not good, K double P divided by T0 plus M omega S minus M omega S tau by half. Yes! I finished this formula. It's look terrific. Looks terrific, isn't it? In general, it's not so terrifying, but I need to draw it. Frequency okay, double P by tau, 4P by tau, here will be 6P by tau. It's a borderline. Inside, maybe I draw it in red. Main lines of the pulse sequence. This line, for example, this is double P divided by T0. This is 4P divided by T0. This one is 6P divided by T0. 8P. So this border line is defined, white line, by general, by tau, by length of the pulse. And spectral line, these central lines, are defined by pulse period. Outside of them, you will see lines. This will be plus 1, 2, 3, blah, blah, omega s. This will be minus 1, 2, 3, blah, blah, omega s. You will see lines as we saw on FM signal. This blue part this one equals to frequency modulation of our transferred signal with the frequency modulation. This kind of modulation, see that's the problem. It's very good for near communication, but if you try to use it on a long range, you'll see extremely ineffective, but it's extremely ineffective. And remember frequency modulation, the deeper modulation, the wider was this omega 0. It was something like this. Yeah? Remember when I show FM signal? You see white bands around your pulses. So this type of signal transfer, this area is one to one as a frequency modulation of this with this our transferred signal. Not so nice. It's good for from the air intake to the MCU. 2 meters, 2 meters. It's fine. But when you try to use it on a long distance, no. It's not a good idea. One more. More terrifying formulas, forgot of terrifying formulas. If we use only frequency, so when time between pulse is fixed, we will get a bit different spectrum. The previous one is for phase shift. This one be different when only frequency change. This will be tau divided by T0 plus 2 divided by T sum 1 to infinity sine omega 0 tau by half multiplied by Bessel function. Here should be m omega signal divided by omega 0 m omega 0 cosine n omega s t minus tau by half plus will continue. Yeah, can I continue? Plus 2 divided by 3 sum n from 1 to infinity sum the m from minus infinity to infinity sine of omega 0 tau by half. Here should go Bessel function of n omega 0 plus m omega signal divided by omega 0. Wait. Multiplied by m omega 0 cosine of n omega 0 plus m omega s time minus n omega s tau by half. 1, 2, 3. Yeah! Nice formula. Tiny little formula. And one more modulation remains. Most popular of them all. Used everywhere. Simple. It's all around us. It simply overtakes this world. Can I? This world is simple, coursed with PWM, pulse width modulation. In pulse width modulation, tau is a function of signal. In the simplest case, tau at the time will be some kind of tau 0 plus m s not t. Here, now, I have a pure sequence. I can repeat it. At this moment, tau is 20%. Look at the spectrum. Tau is 40% of T capital. 50, they are equal. 71, there is the spectrum. But why it's so popular? You see? Today, electronics is all around us, and all electronics need power supply. Most of nowadays is a PWM-based power supply. Idea: you have, okay, AC input, put a rectifier to convert it to DC, and then switch transformer your load voltage. This switch PWM UFB, feedback voltage. And yeah, it's a good idea to put a snubber here. Why? What? Ooh, snubber is important. First you need to discharge somewhere energy, but also you can simply put a diode. You need losses to you need to cut this tail. Otherwise, you will pollute with you will not pass electromagnetic compatibility test. You need to cut, this tail goes up to mega. It's reality, you will 10, 12 megahertz without snubber. You need to cut this long tail of, for this system it will be disturbance. What's the mass here? Where is something? Something, for example, power supply of TV. Transformer, here, switch. This one, optocoupler feedback. And where is the filter? Here, double coils. Take one filter with double coil, second filter with double coil. Or one for failure of EMC compatibility. One moment I will show it in reality. But please don't do it at home. Really. Get my tiny victim.
That's the one. That's the one.
Oh my goodness.
Here is my tiny victim. It's for power supply from cash register. Yeah, here it is. It's a real voltage of the PWM-based power supply. This one else with it's so-called quasi-resonance. It allows those primary winding contours to oscillate for some time. Look what's the reaction to the load change. What I'm doing. I'm increasing load. I'm decreasing load. Increase, decrease. You see what happens? Changes the area of pulse. How it works? For example, time, it's internal control. Let's draw a line. It's what I'm doing. It's a feedback voltage. Q, the state of the switch. Let's now assume what load decreases. If load decreases, voltage rises. Yeah? L prime higher than L load. And see what happens. Pulse will be shorter. Transformer primary coil receives less energy. And voltage what? Goes down. Load decreased, load increased. Load decreased, load increased. Load decreased, load increased. You see how changes the area? By the way, here is a bit different schematic. This thing is a switch like this, and we are looking at this voltage. Check the area. Energy load decreased, area decrease, and voltage remains the same. Load increase, area wider. Look how this thing will react on primary voltage change. You know, I can draw an opposite. For example, voltage decreases. We will get wider pulse. Take a look how this thing reacts. Voltage 240 volts. See, amplitude high, but area remains the same. In opposite, 150 volts. I decrease primary voltage. Amplitude lesser, but area remains the same. Pulse width modulate maintain constant amount of energy transformer received. You see? Area of the pulse remains the same. It's the way how to get a stable voltage, but that's not all. Wait 1 second, I'll bring another one. I have another big thing. All kind of step up and step down converter. LED and luminescent drivers. All they. Rely on PWM technique. And where is my signal? Here is my signal. This version is for high load more powerful. Plus DC minus DC. It comes with two switches. For higher energy. Whoop, whoop. See, I change voltage, 150 volts, 250 volts. But the area of pulse remains the same. What it of, just to understand, this small transformer, it's from computer power supply, it's for 150 kilohertz or 200 kilohertz. 100, no, this was 300 watts power supply. This transformer for 50 hertz has the same ratio. Imagine you carry this with your laptop. It's without cooling, without rectifier, without filter. It's for 50 hertz, for 200 kilohertz. In general, energy density changes approximately as frequency power 4. To make thing small and portable, you need to increase frequency. And you need to keep energy flow. Under control. You need stable voltage. But PWM means you saw spectrum of the this cache register. Switch back. This one is more, how to say, AMC tolerant. Here it is. Signal. Each division is not 10 volt, it's 100 volt. So peak to peak, 200, 300, 400, 500 volts. Please never ever touch PWM-based power supply without training and equipment. This thing flowing through your hair means painful death in 50 minutes. They are really dangerous. And to understand, come on. Spectrum. Where is my cursor? 100 kilohertz base conversion frequency, and tail can be observed here it ends at 6 megahertz. Here is the tail of unfiltered. It has input filter. It's not polluting network, but real spectrum of this ends somewhere at 7 megahertz. That's when your EMC compatibility challenge starts. If you work with high-end acoustics or, for example, medical equipment or something highly sensitive, this tail will be your pain. Here it is, PWM-based power supply. Think not to play with without proper training and proper equipment. 7 megahertz. From base frequency of 100 kilohertz. And today they are everywhere. It's strange, but this larger power supply from PC or I don't know, some chargers are less dangerous than this things like phone charger. Yeah. Small phone charger can kill you. It causes so-called fibrillation of your head. And if someone don't bring this nice thing, Hollywood guys very love them. Clear discharge. This thing sets a special craft pulse through the head to restore its normal operation, because it's all is driven by electrical signal. If you get this pulse through 15 minutes and
So you said how can this phone charger be dangerous? How can it be dangerous? Because doesn't it give the output of about
output is isolated and only 5 volts. But if you put your finger on a primary, on a hot side, you have all chances to end your life. Primary side is the I saw versions with 800 volts of peak.
How can you put it when it is covered?
It's special welded to be unopened.
So you say
It's if you take modern one, you see no screws. You cannot open it.
they said the voltage can go as 800 volts.
Yeah, up to. This one has peak to peak 5 from cash register. I saw version where when switch closes, higher point 800. Really?
And that is the primary side.
Yeah, it's on the hot side.
Yeah.
This.
So we are supplying to
You get it? For me, I'm like,
What can be done with the chisel? This part secondary is not dangerous.
yeah.
Here is a nice black line, input filter, input DC capacitor, switch, and this nice transformer. On a primary here, on the primary side of transformer,
It goes up to
from 3 to to 5, sometimes even 800 volts.
Why?
Because the self-inductance
Self-inductance.
of the primary coil, when this switch closes, there will be a high pulse. Don't try this at home without training, really.
What can you just try and check the voltage?
Here,
Like at home, try to check the voltage and see if it is.
write your testament and start. Believe me, it's not a toy. You know what's written on computer power supplies? No serviceable parts inside. Keep your finger off. Without equipment and training. First training, then equipment. Okay. I don't see many people online. Maybe they